Great. Okay, so my name is Jacqueline Buros. I work at Generable, and I'm going to be talking about semi-mechanistic Gaussian process regression models today. Our goal is to estimate treatment effects on tumor size, and this is a problem that's been in the works. A lot of people have been working on it for a long time, but we think we made some advances in a hard area, and I'm happy to share them with you today. So first, most of the models I'm discussing today were implemented by my colleague Juho Timonen. If you have technical questions or you're curious about the work, you can also speak to him. He's here today and right back there. And so I largely motivated the project and did the applied work. And so I think that division of responsibility is important to highlight. So imagine you are analyzing data from an oncology clinical trial. You have 30 patients on treatment, 30 patients randomized to standard therapy. We measure the patient's tumors every 12 weeks with a CT scan up until they stop treatment or they withdraw from the trial or they have an adverse event or a number of things can happen. So the key research question that we're trying to answer is which treatment is most effective? And there are standard ways of answering this. Every phase 2 clinical trial faces this question. Some of them work better than others. There are two main problems we're trying to solve. One is this small sample size problem. With only 30 patients, patients are very different with cancer. They come in with all sorts of prior treatments, risk factors. And the second problem is that many of them stop therapy, and so we lose the data. So we have this informative censoring problem. So these are the two tricky things about this. And a lot of the methods that are used kind of ignore these. But this is an area that we think a lot about. So just for those who haven't seen it, tumor size data looks something like this. We center everyone by their baseline value. We track them over time. And in this particular case, this is a chemo drug. A lot of patients respond, and then they rebound, right? The tumors start growing again. So this is a very typical pattern. And we typically fit it with a mixture of exponentials that describes this pattern where tumors shrink and then they grow, right? So we have two terms. There's the shrinkage, the Ks that defines this rate of shrinkage, and the Kg that defines this rate of growth. And all is well and good. However, there are some problems with this. When we fit the chemo data to this model, it fits beautifully. So great. One of the problems is with newer targeted therapies, immunotherapies, we often don't see this canonical response. We often see patients whose tumors first grow and then they shrink because the tumor cells infiltrate the tumor, so it grows, similar to the way that your cut will swell when you get a cut and then it shrinks. Or they have this kind of long-term 5-year remission, which is great. We're really happy to see that, but it kind of doesn't fit our model. And then there's other phenomena too. So we see hyperprogression, patients whose tumors, for whatever reason, when they undergo chemotherapy, their tumors grow wildly, and they don't shrink, they just keep growing. And this is an adverse reaction to the drug. So we see this problem of a lot of curves that just don't fit this problem of shrinkage and rebound. An assumption of the model is that all tumors will grow back. That's a problem for us when tumors don't grow back. And then the second phenomenon we see is the green line where a tumor shrinks and then stays steady at some base rate, again, for 5-10 years, which is also a good outcome. But this kind of plateau and growth and shrinkage is also not something the model form that we're using really supports. So as more and more therapies come on board, like CAR-Ts and bispecifics, we're seeing even more heterogeneity in the response profile. So the question we've been thinking about is, do we just keep adding new models to describe these effects, or do we need a different approach? The second problem we see is heterogeneity of response. So this is an example of an immunotherapy where you have either patients who are hyperprogressing or shrinking and staying shrunken. So your typical hierarchical model with some distribution over patient effects doesn't fit that well, because when you look at the patient-specific effects, it's very bimodal. And so then this is the other problem. So we've been playing around with, like, do we fit a mixture model? How do we address this problem? We get the average effect right, but the average doesn't actually describe any patient. So this is the challenge. So this is the motivation behind the SFGP package. It's an R package. It works similar to BRMS. You're going to specify your model. It's going to write out the stand code for you. It's going to give you a lot of functions to prepare the data and prepare the output. It is kind of in progress, so like a lot of the functionality is there, but we definitely want feedback on it. And we're thinking about if it's useful, whether to continue to maintain it, and all this kind of stuff. So definitely let us know. It's on GitHub. So the rationale behind this is that you build up your model as you sort of start with, let me fix the math on this. Excuse me. Math renderer. Yeah. And then SVG. Yeah. Nope. Yeah, there it is. So we start with the likelihood model, pretty basic, log normal noise. And then we build up our model as a sum of terms. So here, J is indexing the terms, and F is the function for each term. So we start with a baseline value. Every subject has a baseline value. We could build up a model for this. We typically don't. We just estimate it for each patient. There's an SF term, which is the same as the one we just saw. We can define this by ID or by ID nested in ARM or by any level of hierarchy that you might be curious about. And then we have two Gaussian process terms. So the first is going to put a Gaussian process on the noise. So if you did an SF plus the GP model, then you're modeling the mean function is your SF, and the noise function is this GP. And this uses the Hilbert space sort of approximation to the GP, just because we often do have hundreds of patients. And then furthermore, you can have this be sort of defined by category. So we often want to fit the GP per treatment arm, because that's the effect we're most interested in, is characterizing the distribution of responses by arm. There are other terms that I didn't describe here, like Emax, that sometimes we use when we're looking at PK data. So this is quite a flexible framework to just keep adding different terms to the model. So we're going to look here at 3 candidate models. We're going to fit it to simulated data that recapitulates some of the problems that we see in practice, and then I'll show you some of the results. So that's kind of the rest of this talk. The first model is the standard SF model with effects per ID and ARM. The second is this SF plus a GP term. So here we're fitting the GP to time by arm, right? After using the SF as the mean function. And then the final model is one that is another way that the package supports specifying the model, is where instead of putting the GP sort of after the SF, we're going to put it inside of the KS term. So here I'm saying that KS has an offset per ID and per arm, and it also has a GP term over time per arm. So now we're allowing KS to vary over time differently for each arm, and we're allowing KG to vary over time differently for each arm. And so these are kind of different approaches with these standard terms of how we can build up our model for tumor size. And it's quite simple to also add a GP per sex or per biomarker or per other characteristic, age that might be of interest here. So each of these pieces can be kind of customized to your research question. Something that we often do is put in an Emacs term for exposure to drug, and we'll couple it with the PK/PD model. So there, you can adapt it to your use case. Okay, so now we're going to fit these 3 models to our data. We have 4 simulated treatment arms, and these are the simulated data. They're not simulated according to an SF model. They're not simulated according to any of the models that we've implemented here. This is actually a mechanistic model, like a pretty complicated ODE model that was provided to us by a sponsor that really mimics like the drug action in question. And a challenge here is we do have this heterogeneity of response with some hyperprogressors and then we see a lot of this sustained response. And in the internal testing, these dynamics really match what they see in their tumor data. That's what we've been told. And we kind of, looking at the data, it looks about right to us. The thing that we actually care about characterizing is these progression events. And in the standard way these are presented, they're often easy to miss. So I like to put like a point at those moments just to draw the attention to how frequently they occur and under what circumstances. So if we fit our standard SF model to these data, it does an okay job. I would not call this a great fit. These are 50 and 80s, and it is, if you add the measurement noise, it's well calibrated. I'm not happy with that, let me say. And this gets worse when you look at the patients whose tumors grow, because you'll see patterns like this, where it's taking the mean response, which is to shrink, and kind of fitting it to the 2 observations we have. And we have this problem of, because the growing tumors are censored, and they only have 2 records, and our sustained response tumors have like 10, 20 measurements, there's this weird phenomenon where any patient who's growing, the model thinks, no, that's probably an error. And it's actually not. This is 100 millimeters of tumor growth. That's significant. This is not an error. So when we fit these to the SF plus GP model, we're able to recover this heterogeneity of response. And this is actually really encouraging because this is the model where we're fitting the GP to the noise. And it's helpful to know that even in this case, we're able to recover the sort of the mean function for each of these patients. The model's kind of representing our view of reality. And this gets even better when we put the GP inside the KS and KG terms. Because here we're saying the KS and KG may vary over time in different ways per arm, but they're not varying over time in different ways per subject. So the subject level sort of heterogeneity, we're kind of characterizing the arm level response with the greatest specificity that we can with this model. And we do recover, like these, we can barely even see the interval. And when we add measurement noise, it's well calibrated, it's well behaved. So this is actually what we want. We want the mean function, the linear predictor, to really recover the pattern that we think is true in the data. And when we look at the Lu scores, this alternate SFGP, where we bring the GP terms into the KS and KG, really outperforms the other 2 models. It's a really clear difference. So this is also encouraging to us. But it's not quite enough for what we want. We want to simulate treatment effects. So the end goal is to actually generate a sample of 100 patients that reasonably reflect the distribution of responses we would expect a sample of 100 patients to show, right? We want to be able to say, oh, approximately 20% are going to be hyperprogressors. This is the typical duration of response. We want to compute on these simulations. And when we use the SF model, we have this problem. There's this sort of there's this point in the SF model where it's like very, it jumps when the predicted value goes above, it starts growing, there's like certain combinations of terms, and it's not continuous. Like it's not like you move KS one step and all of a sudden it's growing. Like it's in a different space of those two parameters. So we have this problem that it's very hard to get the model to continuously have a slightly shrinking tumor to a slightly growing tumor. But in this SFGP model, we can simulate tumor trajectories that look pretty realistic. So when we compare these to our observed data, our simulated data in a larger sample, we get a pretty good, very good distribution of depth of response, less good distribution of duration of response, but still very, very close to what we see and better than we've seen in the past. And then this is the version with the alternate model where we pack KS and KG in. And so one problem we found here is that in order to get these hyperprogressors, the KS values or the KG values are just too high for the rest of the population. So we think by packing it in, it sort of better represents. This is the best recovery of the treatment effects that we see in this simulated data. So the reason we're using simulated data is because in the real population, when you only have 30 patients, we don't really know what we would have seen had we had 1,000 patients, right? So like using simulated data gives us this grounding in truth. But we do see good performance in real data as well. And these look even more realistic when we simulate the censoring process. It's not surprising the model is a little weird after the censoring moment, but that's okay for what we need. So this is a little like detail in what's going on in this KG model and KS. So where KG and KS are allowed to vary over time, that both of the parameters sort of shrink differently by arm as time goes on. And I think this is how we're getting this like sustained response part of the curve, because the model, like the KG and KS, are becoming less and less relevant as time goes on. And then the last bit is just to show the distribution of depth of response. So fit1 is the SF, fit2 is SF plus GP, and fit3 gets pretty close both to this observed sample and like the true distribution. And particularly, we're able to characterize the frequency of these growing tumors. And the last bit is this time to progression. And the SF model actually gets the direction of effect wrong, where it assumes more progressors in the higher treatment effect group. And so at least fit 2 and 3 have the right direction of effect. And so that's where I'll end. If there are any questions, we're happy to take questions, and then here are the references to the work. Mm-hmm.
And is there a sense of kind of how early in the process you could actually, like, you would have enough data to start applying this?
Mm-hmm. So a couple points. So the first question is about the use case. And we do actually use it in those two cases you mentioned, both in assessing the presence of a treatment effect, but also in sort of simulating the next trial and helping with trial planning. And then I would add another use case and a little detail. The first is it's not only assessing the presence of a treatment effect, but very often a company will have 5 or 6 compounds in development, and they have to kind of pick 2. So it's also a question of which 2 do you pick. And so it's the relative strength of treatment effect as well as the presence. And then a third use case is around identifying the population most likely to benefit. So this is where the ability to include covariates or test for effects according to prior lines of therapy or gender is actually very helpful, because then they can say, we do see evidence that it's stronger in patients with this biomarker instead of this biomarker. And that becomes really difficult at these small sample sizes. The second question about how early, this is something we are testing. So we've done this work with as few as 7 patients. What we want to see are well-calibrated estimates. So it really does depend on the homogeneity of the response. If it's very heterogeneous, we'll be uncertain. And then we often, similar to Sebastian's talk earlier, we are often bringing in external control data in that context. So when we have very few subjects, we often don't have a control arm. So this is the other reason we want to be able to accurately simulate the distribution of responses, is so we can bring those simulated records in as a control arm in another context. Mm-hmm. Yeah?
Yeah, the question about data science, like how little of the trajectory do you need to see in order to make early sensible decisions? Because typically you don't want to wait 500 days to make a decision.
Right. This is exactly a problem. We often are truncating the data. So if we have a data set that looked like this in the real world, we would be testing it after a year follow-up, after a 6-month interim analysis to try to see. If we have previous data that we can use to kind of inform the priors for the expected trajectory, we can make that assumption, but we definitely want to test the validity of that assumption. The other thing that we're really interested in is the potential for other biomarkers like circulating tumor DNA to help us get better at predicting the future trajectory, even if it's not observed. But with this kind of data, those are the 2 options that we've seen. There are classes of drugs. So when we fit like a meta-analysis model, we'll look at chemo, targeted therapy, immunotherapy. And for the same early signal, the immunotherapy drug tends to be more durable than the chemotherapy. And so those are examples where we can kind of make an assumption, be very clear about the assumption, and then present the data with kind of the most conservative and the most anti-conservative view and let them decide. But it is very tricky if we have short follow-up. It's helpful. Typically what you have is the first patient in will have the longest follow-up, and then you have this kind of fewer and fewer patients with follow-up. And so this is a scenario we test. And what we see is at least we do have well-calibrated estimates. Because we're using this SF model that assumes that patients are going to rebound, when we have only a couple measurements, the model tends to assume they're going to rebound, even if we see over time, when we get the next data cut, they actually were sustained. So if anything, it's more conservative. And this is one reason we don't like just using only GP, because we think you need this mean function to kind of say the tumors have this tendency to grow.